Hello, friend. Welcome back to this quiet corner of the night. Some evenings when the sky stretches endless and dark, it's easy to believe the universe is still, silent, peaceful even. The stars blink softly scattered like forgotten breath across velvet. Light years away, galaxies turn in slow ancient waltz. Everything feels calm. Everything feels gentle. But that stillness, it's a kind lie the cosmos tells. Because out there in the vast cathedral of space, the universe doesn't whisper. Sometimes it screams. Sometimes it tears reality apart with forces so immense, so violent, that even light itself bends, breaks, and runs away. Events happen out there that could vaporize entire solar systems in the time it takes you to blink. Explosions brighter than 1 billion suns. Collisions that ring through the fabric of space-time, like thunder through an empty cathedral. Tonight we're going to drift through the most powerful events the universe knows how to create, not to frighten you, not to overwhelm, just to remember quietly that we live in a cosmos capable of unimaginable beauty and unimaginable violence. Before we begin, if you find comfort in these quiet journeys through the stars, you might like to stay a while. You can gently tap the like button, subscribe if you'd like more stories, told softly, and ring the little bell, not for noise, but so the next quiet night can find you again. Now let's drift. Think about this for a moment. Every atom of iron in your blood was forged inside a dying star. The calcium in your bones, the oxygen you're breathing right now, even the gold in a wedding ring, all of it was created in moments of cosmic violence so extreme they defy imagination. We are quite literally made of stardust, but not gentle stardust. We're made from the shrapnel of explosions, from the screaming deaths of giant suns, from collisions between objects so dense that a teaspoon would weigh more than Mount Everest. The universe built us from catastrophe, and tonight we'll meet 7 of those catastrophes. 7 types of events where the cosmos remembers how to scream. The first thing you need to know is this power in the universe isn't what we think it is. We measure explosions on Earth in kilotons, megatons. The atomic bomb dropped on Hiroshima released energy equivalent to about 15,000 tons of TNT. It flattened a city. It changed history. It was by human standards an almost incomprehensible release of energy. But in cosmic terms, it was barely a whisper. Scientists measure cosmic events in something called ergs. 1 erg is a tiny unit of energy, about the force needed to lift a mosquito 1 centimeter. It sounds small, but when you're talking about the universe, you're not counting in millions of ergs, or billions, or even trillions. You're counting in numbers with 50 zeros behind them. Numbers that don't have names in most languages. Numbers that make our brains glitch trying to comprehend them. The Hiroshima bomb released about 10 to the power of 21 ergs. That's a 1 with 21 zeros, again devastating by Earth standards. But a supernova, the death of a massive star, releases 10 to the power of 51 ergs. That's a billion times more energy. In a single moment, a dying star can outshine its entire galaxy of 200 billion suns. For just a few weeks, 1 star becomes brighter than hundreds of billions of stars combined. And that's not even the most powerful event we'll talk about tonight. Here's something remarkable. These events happen all the time. Right now, as you rest here in the dark, somewhere in the observable universe, a star is exploding. A black hole is devouring matter and spitting out jets of energy that travel at 99.9% the speed of light. Neutron stars are colliding, creating ripples in space-time that wash over us like invisible ocean waves. The universe is never still. It's constantly erupting, colliding, tearing itself apart and rebuilding from the wreckage. But distance is our guardian. Space is so vast, so impossibly mercifully vast, that most of these cosmic screams never reach us as anything more than a gentle photon tickling a telescope somewhere. Light takes time to travel. When we look at distant galaxies, we're not seeing them as they are. We're seeing them as they were millions or billions of years ago. That star that exploded last Tuesday in some distant galaxy, Its light won't reach Earth for another million years. And by then, our sun will be a different age. Our planet will have turned a different face to the cosmos. Time and space protect us. They wrap us in layers of distance so thick that the universe's violence becomes bedtime stories, becomes science, becomes something we can study with wonder instead of fear. But imagine for a moment if that distance collapsed. If a gamma ray burst, one of the most powerful explosions known to physics, happened not thousands of light years away, but right here in our cosmic neighborhood, say a few dozen light years from Earth. We wouldn't see it coming. Gamma rays travel at the speed of light. The first warning would be the last warning. The sky would flash brighter than 1,000 suns, and within seconds our atmosphere would begin to burn away. Not from heat, but from radiation, so intense it would shatter the molecular bonds that hold nitrogen and oxygen together. The ozone layer, that thin shield protecting all life on Earth's surface, would simply cease to exist. Scientists suggest that a gamma ray burst might have been responsible for one of Earth's mass extinctions, the Ordovician extinction about 440 million years ago. No one knows for certain, but something killed off 85% of marine species in a relatively short period. And the pattern of extinction species dying at the ocean's surface while deep-sea creatures survived matches what you'd expect if Earth's protective ozone layer suddenly vanished. The universe has a long memory of violence, and Earth bears quiet scars from events we'll never fully understand. But here's the beautiful paradox. These moments of destruction are also moments of creation. When a massive star explodes, it doesn't just destroy, it builds. Inside that inferno, elements are born. Carbon, nitrogen, oxygen, silicon, iron. All the heavy elements that make planets possible, that make life possible, are forged in the final moments of a dying star. The explosion scatters these elements across light years of space, seeding new clouds of gas and dust that will eventually collapse to form new stars, new planets, maybe new life. Death becomes birth. Violence becomes creation. The universe doesn't waste anything, not even catastrophe. We tend to think of space as empty, and most of it is. The average density of the universe is about 6 hydrogen atoms per cubic meter. That's remarkably close to nothing. But between those atoms, between the stars and galaxies and vast cosmic voids, there are echoes. Leftover light from the Big Bang, still washing over us, cooled now to just a few degrees above absolute zero. Neutrinos from distant supernovae passing through your body, right now, trillions of them every second, barely interacting with matter at all. Gravitational waves from colliding black holes stretching and squeezing space-time by less than the width of a proton. The universe is quieter than we imagine, but it's never truly silent. Even in the darkest, emptiest regions of space, there's always something happening. Always some faint signal, some distant cry reaching across billions of years to touch us here, now in this moment. And that's what makes studying these events so profound. We're not just learning about physics. We're not just measuring energy and distance and time. We're listening to the universe tell its own story. We're hearing echoes of events that happened before Earth existed, before the sun formed, before our entire solar system was anything more than a cloud of dust orbiting a galaxy. Every telescope pointed at the sky is an ear pressed to the cosmos, listening for its secrets. Here's a question worth pondering as you drift towards sleep. Why do we care about these events? Why spend billions of dollars building telescopes and satellites and detectors to study explosions so far away they can never hurt us? Why does it matter that 2 black holes collided 7 billion years ago? Maybe because understanding violence helps us understand peace. Maybe because witnessing destruction helps us appreciate creation. Or maybe it's simpler than that. Maybe we study these events for the same reason we tell stories around campfires, the same reason we write poems about stars, the same reason you're here tonight, listening to a voice in the dark talk about the universe. Because we want to know, because we need to know, because somewhere in our DNA and those atoms forged inside dying stars, There's a longing to understand where we came from, how we got here, what this all means. The universe doesn't owe us answers, but it keeps offering them anyway. In the light from distant explosions, in the ripples of colliding neutron stars, in the quiet mathematics that describe how black holes eat reality itself. And so, tonight we'll listen. We'll drift through 7 cosmic catastrophes one by one. We'll start with gamma-ray bursts, the brightest explosions since the Big Bang. We'll watch stars die in supernovae, creating the elements that would eventually become you and me. We'll witness neutron stars colliding in explosions that rain gold and platinum across the cosmos. We'll peer into the violent hearts of quasars, where supermassive black holes devour suns and spit out jets of energy. We'll feel the tremors of magnetar flares, where magnetic fields 1,000 trillion times stronger than Earth's snap, and release more energy than the sun will produce in its entire lifetime. We'll sense the ripples from merging black holes events so violent, they create waves in the very fabric of space-time. And finally, we'll stand at the edge of the beginning itself, at the Big Bang, the event that started everything, the moment when time and space and matter all began. These are the moments when the universe remembers how to scream, but they're also the moments when it remembers how to create, how to build, how to transform nothing into something, darkness into light, simplicity into complexity. You don't need to understand all the physics. You don't need to memorize the numbers or the equations. Just let yourself float here in this quiet moment and feel the scale of it all. Feel how small we are, and somehow how perfectly sized to witness it. Because here's the final truth. Before we begin, we are not separate from these events. We are made by them, shaped by them. Every breath you take contains oxygen forged in a supernova. Every thought firing through your neurons relies on carbon created in a dying star. You are not just studying the universe, you are the universe studying itself. And that perhaps is the most powerful event of all. Now, as the night deepens and the stars continue their ancient dance, we turn our attention to the first of these cosmic catastrophes, an event so bright, so violent, so impossibly energetic, that for a few brief seconds, it can outshine everything else in the observable universe combined. An explosion that happens when the biggest stars meet their end in the most dramatic way possible. We turn now to gamma-ray bursts, the universe's dying breath, scattered across billions of light years and billions of years waiting to tell us their story. Picture this, October 9th, 1963. Cold War tensions run high. American military satellites orbit Earth, waiting for the flash of Soviet nuclear tests. The Vela satellites, they're called, designed to detect gamma radiation from atomic explosions. Their mission is surveillance, not science. They're looking down at Earth, watching for signs of war. But on this particular day, something unusual happens. The satellites detect gamma rays, powerful bursts of radiation. But they're not coming from Earth. They're not coming from the atmosphere. They're coming from above, from space itself, from directions that make no sense. The military keeps this secret for years. They don't know what they've found. They don't know how to explain it. And honestly, they're probably a little frightened by it. It's not until 1973 that the data is finally declassified and published. And when astronomers see it, they realize something remarkable: the universe has been screaming at us, and we've only just started listening. These signals, these mysterious bursts of gamma radiation, would come to be known as gamma-ray bursts. And they remain to this day the brightest electromagnetic events known to occur in the universe since the Big Bang itself. Imagine holding all the energy the sun will produce over its entire 10 billion year lifetime. Now, imagine releasing all of that energy not over billions of years, but in 10 seconds. That's a gamma-ray burst. In those few seconds, a single event can outshine the combined light of every star in a galaxy of 200 billion suns. The numbers stop making sense. The analogies break down. Language itself struggles to contain the scale. For decades after their discovery, gamma-ray bursts were a complete mystery. Astronomers could detect them, could measure their energy, could track where they came from in the sky, but they had no idea what caused them, no idea how far away they were, no idea what cosmic machinery could possibly generate such immense power. Some scientists thought they might be relatively close, maybe within our own galaxy, just smaller and less energetic than they appeared. Others suspected they came from the edge of the observable universe, which would make them far more powerful than anything previously imagined. The debate raged for years. Conferences were held, papers were written, theories proposed and discarded. Then in 1997, everything changed. A satellite called Beppo-Sachs detected a gamma-ray burst and for the first time managed to pinpoint its location precisely enough for ground telescopes to observe the afterglow. What they saw was remarkable. The burst came from a distant galaxy, billions of light years away, which meant the energy involved was even more staggering than the most optimistic estimates had suggested. We now know there are two main types of gamma-ray bursts, and they come from very different sources. The distinction is simple duration. Short bursts last less than 2 seconds. Long bursts can last anywhere from 2 seconds to several minutes. Same phenomenon, same blinding flash of gamma radiation, but different cosmic deaths creating them. Long gamma-ray bursts, scientists believe, come from hypernovae. These are the deaths of the most massive stars in the universe, stars 5080, maybe 100 times more massive than our sun. When these giants exhaust their nuclear fuel, they don't just collapse, they catastrophically implode. The core crashes inward, forming either a neutron star or a black hole. And in that moment of formation, if conditions are just right, if the star is rotating rapidly enough, jets of matter and radiation punch through the collapsing star's poles at nearly the speed of light. These jets are narrow, focused like cosmic blowtorches cutting through the universe. If Earth happens to lie in the path of one of these jets, we see a gamma-ray burst. If we're off to the side, we might see a bright supernova, but we'd miss the burst entirely. It's a matter of cosmic geometry of being in exactly the wrong place at exactly the wrong time. Short gamma-ray bursts are different. They're even more violent, in some ways even more exotic. Research suggests these come from the collision of two neutron stars, or a neutron star colliding with a black hole. Imagine two objects each containing more mass than the sun, each compressed into a sphere just 20 kilometers across, each spinning hundreds of times per second, spiraling toward each other through warped space-time until they finally merge in a cataclysm that briefly makes them the brightest objects in the universe. The merger lasts less than a second. The gamma-ray burst that follows lasts a few seconds more, and then it's over. The light fades, the radiation disperses, and all that remains is a new black hole quietly settling into its existence, surrounded by an expanding shell of exotic matter scattered across light years. Here's what makes gamma-ray bursts particularly terrifying, at least in theory, their directionality. Because the radiation is focused into jets, you don't get much warning. If a gamma-ray burst is pointed away from you, you might never know it happened. But if it's pointed toward you, the first photons to arrive are the gamma rays themselves traveling at light speed. There is no early warning system, no time to prepare. The information that the burst is happening arrives at the same moment as the burst itself. Now, before you start worrying, let's talk about distance. The closest gamma ray burst we've ever detected was about 600 million light years away. That's incredibly far. Far enough that the radiation, while still detectable, poses no threat to Earth whatsoever. Our atmosphere absorbed it completely. Life continued undisturbed. But what if one happened closer? What if a massive star in our galactic neighborhood, say within a few thousand light years, went hypernova and aimed its jets in our direction? Scientists have run the simulations. They've done the math. And the results are sobering. A gamma-ray burst within 3,000 light-years could damage Earth's ozone layer significantly. One within 1,000 light-years could strip away half of it in seconds. The radiation wouldn't kill us directly. We wouldn't feel heat or pain. We wouldn't even know it had happened. But in the days and weeks that followed, as solar ultraviolet radiation poured unfiltered through the damaged atmosphere, ecosystems would begin to collapse. Phytoplankton in the oceans, the base of the marine food chain, would die. Plants on land would struggle, and anything that couldn't find shelter would face radiation levels incompatible with life. Some scientists point to the Ordovician-Silurian extinction event about 445 million years ago as a possible gamma-ray burst victim. The extinction pattern fits species living near the ocean. Surface died in massive numbers, while deep-sea creatures survived. It's as if something had suddenly removed Earth's protective shield, exposing surface-dwelling life to deadly radiation, while leaving the depths untouched. A gamma-ray burst would do exactly that. We can't prove it, of course. The evidence has long since dissolved into deep time, but the possibility remains a reminder that we live in a universe capable of casual violence on scales we can barely imagine. The good news, if you can call it that, is that gamma-ray bursts are rare, incredibly rare. In our entire Milky Way galaxy, we might expect one long-duration burst every few million years, and the odds of it being pointed at Earth are tiny, a fraction of a percent. The galaxy is vast, space is mostly empty, and the chances of being in the wrong place at the wrong time are mercifully small. But they're not zero. They've never been zero, and they never will be. Every moment somewhere in the universe, a massive star is collapsing. Somewhere neutron stars are spiraling toward merger. And somewhere gamma-ray bursts are lighting up the cosmos like cosmic flashbulbs, their radiation spreading outward in narrow beams, traveling across millions and billions of light years, carrying news of ancient violence to anyone watching. Here's something beautiful about gamma-ray bursts. They let us see farther back in time than almost any other phenomenon. Because they're so bright, we can detect them from the very edge of the observable universe. The most distant gamma-ray burst ever recorded happened just 630 million years after the Big Bang. Think about that. The universe was only 4.5% of its current age. The first galaxies were still forming. Stars were different back then, more massive, burning hotter and faster. And we can see them dying 13 billion years later, their death screams reaching us as faint whispers of gamma radiation. Each burst is a time capsule, a message from the ancient universe telling us what conditions were like when the cosmos was young. The light that reaches us has been traveling for so long that the galaxy that produced it might not even exist anymore. We're seeing ghosts, echoes. The after images of violence that happened before Earth existed before our sun, formed before any of the planets in our solar system had even begun to coalesce. You might wonder, how do we actually study these things? How do you investigate an event that lasts seconds, happens billions of light years away, and never repeats in the same place? The answer is patience technology and a network of satellites watching the entire sky at once. The Swift satellite launched in 2004 can detect a gamma-ray burst, calculate its position, and swing its telescopes to observe the afterglow within 60 seconds. 60 seconds. From detection to observation in the time it takes to make coffee. And what Swift sees is remarkable. After the initial gamma-ray flash fades, there's an afterglow. X-rays first bright and intense, then fading over hours. Then visible light, the glow dimming, but persisting for days or weeks. Sometimes radio waves lasting even longer. Each wavelength tells part of the story. Each observation adds detail to our understanding of what happens when the universe's most massive objects meet their violent ends. The more we learn about gamma-ray bursts, the stranger they become. Some bursts show evidence of jets traveling at 99.995% the speed of light. At those speeds, time itself behaves oddly. Particles in the jet experience time dilation so extreme that seconds for them could be hours in our reference frame. Matter in these jets isn't just hot, it's relativistic. The atoms are stripped down to bare nuclei, their electrons torn away by sheer energy. Physics in these environments is extreme, violent, beautiful in its intensity. And yet, for all their power, gamma-ray bursts are also creators. The neutron-rich material ejected during short bursts during neutron-star mergers is where many of the heaviest elements in the universe come from. Gold, platinum, uranium. These elements can't be made in normal stellar fusion. They require extreme conditions, unimaginable pressures, temperatures that exceed anything found in regular supernovae. Neutron-star collisions provide those conditions. The gold in jewelry, the platinum in catalytic converters, even the uranium in nuclear reactors, all of it was likely forged in the violent merger of dead stars billions of years ago. We wear the remnants of cosmic catastrophes. We build with them. We power our civilization with them. The violence of the universe becomes through time and distance something useful, something beautiful. There's a kind of humility in studying gamma-ray bursts. Every measurement reminds us how small we are, how fragile, how dependent on cosmic luck. We exist in a brief quiet moment between cataclysms. Our star is stable. Our galaxy is relatively peaceful. No nearby stars are massive enough to threaten us with hypernovae. We are for now safe. But for now is the key phrase. The universe is patient. It's been playing this game for nearly 14 billion years, and it will continue long after we're gone. Does that make you uneasy, or does it bring a strange kind of peace, knowing that we're just passing through just brief witnesses to a cosmos that was violent before us and will be violent after us? Maybe both feelings are valid. Maybe that's part of being human, holding two contradictory truths. At once we matter and we don't. We're significant and we're infinitesimal. We're made of stardust and we're nothing special. Gamma-ray bursts teach us about extremes, about the edges of what physics allows, about the moments when matter and energy and space-time all reach their breaking points. But they also teach us about perspective, about how distance can turn terror into beauty, violence into data, death into discovery. As we drift away from these cosmic flashbulbs, these dying breaths of massive stars and colliding neutron stars, we carry their lessons with us. We remember that the universe is stranger and more violent than everyday life suggests. We remember that we live in a tiny pocket of calm within a cosmos of chaos. And we remember always that the very atoms in our bodies were forged in moments of violence we can only observe from billions of light years away. But the universe has other ways of dying, other forms of cosmic violence waiting to be explored. If gamma-ray bursts are the quick flash, the sudden bright death, then our next event is the slower burn, the collapse that lights up the sky for weeks, the explosion that seeds galaxies with the building blocks of planets and life. We turn now to the deaths that made everything possible, to the stellar catastrophes that created the very elements you're made of, to supernovae, the forges that made you. On July 4th, 1054, Chinese astronomers looked up at the night sky and saw something impossible. A new star, blazing bright in the constellation we now call Taurus. Not a comet, not a planet, a star where no star had been before. And not just any star. This one was so brilliant you could see it during the day. For 23 days, it outshone every object in the sky except the sun and moon. At night, you could read by its light. The Chinese called it a guest star. They recorded its position, its brightness, how long it remained visible. Then gradually, over the next 2 years, it faded, dimmed, and finally disappeared from view, entirely leaving the sky exactly as it had been before. As if nothing had happened, as if the universe had simply been trying on something new and decided it didn't fit. But something had happened, something extraordinary. What those astronomers witnessed wasn't a new star being born. It was an old star dying, exploding, tearing itself apart in a cataclysm so violent that for a few brief weeks, a single dying sun outshone an entire galaxy. What they saw from 6,500 light years away was a supernova. And its remnant, the expanding cloud of gas and dust left behind, is what we now call the Crab Nebula, one of the most studied objects in astronomy. Here's what makes supernovae so fundamentally important to everything: they're not just deaths, they're birthplaces. Inside the core of a massive star during its final moments of collapse, nuclear fusion goes into overdrive. Elements that took millions of years to slowly build up suddenly fuse together in seconds. Carbon becomes neon. Neon becomes oxygen. Oxygen becomes silicon. Silicon becomes iron. And in that brief violent moment when the star explodes, when temperatures exceed billions of degrees and pressures crush atomic nuclei together, even heavier elements form: cobalt, nickel, copper, zinc, all the way up to gold, platinum, and uranium. Everything heavier than iron in your body, every atom of it was created in a supernova. The calcium in your bones, forged in stellar death. The iron in your blood, born from collapse and explosion. The zinc in your enzymes. The copper in your nerves. The iodine in your thyroid. All of it came from stars that died before our sun was born. You are not just made of stardust. You are made of supernova dust. You are built from catastrophe. Scientists recognize several types of supernovae, but two main categories matter most: Type 1 and Type 2. The difference isn't just technical, it's fundamental. It's about how stars die and what they leave behind. Type 2 supernovae are what most people picture when they think of exploding stars. These come from massive stars, at least 8 times the mass of our sun, sometimes much larger. These giants burn through their fuel quickly. While our sun will shine for 10 billion years, a star 50 times more massive might last only a few million years. They live fast and die young, burning bright and fierce until the moment their core runs out of fuel. When that moment comes, everything happens at once. The core, no longer supported by the outward pressure of fusion, collapses. In less than a second, a sphere of iron the size of Earth compresses down to a ball just 20 kilometers across. The collapse is so violent, so rapid, that it releases more energy in 1 second than our sun will produce in its entire lifetime. That energy blows away the star's outer layers in an explosion that can briefly outshine an entire galaxy. What's left behind depends on the original star's mass. Smaller massive stars, 8 to 20 solar masses, leave behind neutron stars. We'll talk more about those later. But the truly giant stars, those above 25 or 30 solar masses, don't stop collapsing. They keep going. The core crushes down past the neutron star stage, past the point where matter can resist, all the way down to a singularity. They become black holes, and in doing so, they remove themselves from the visible universe entirely. Type 1 supernovae are stranger, more subtle in their setup, even if they're just as violent in their execution. These don't come from single massive stars. They come from white dwarfs, the dense remnants of stars, like our sun stars that have already died once in a gentler way. A white dwarf is stable, quiet, about the size of Earth, but with the mass of the sun. It can sit there peacefully for billions of years, slowly cooling, slowly fading into darkness. But if that white dwarf has a companion star, if it's part of a binary system, things get interesting. The white dwarf's gravity can pull matter from its companion. Slowly, over millions of years, it steals hydrogen, accretes it onto its surface, gains mass. And there's a limit to how massive a white dwarf can become. About 1.4 times the mass of the sun. This is called the Chandrasekhar limit, named after the Indian-American astrophysicist who calculated it in 1930. When a white dwarf reaches that limit, something remarkable happens. The pressure at its core becomes so intense that carbon fusion ignites. Not slowly, not gradually, but everywhere at once. The entire star undergoes fusion, simultaneously releasing energy so immense it blows the white dwarf apart completely. There's no remnant, no core left behind, just an expanding shell of gas moving outward at 10,000 kilometers per second, glowing bright enough to be seen from billions of light years away. Here's why Type 1. A supernovae matter so much they're remarkably consistent. Because they all come from white dwarfs reaching the same mass limit, they all explode with roughly the same energy. They all reach roughly the same peak brightness, which means astronomers can use them as standard candles, cosmic lighthouses with a known wattage. If you know how bright something actually is, and you can measure how bright it appears from Earth, you can calculate exactly how far away it must be. In the late 1990s, two independent teams of astronomers used Type 1a supernovae to measure distances to far galaxies. What they found shocked the scientific community. The distant supernovae were dimmer than expected, which meant they were farther away than they should be, which meant the universe wasn't just expanding, it was accelerating. Expanding faster and faster over time, driven by something we now call dark energy, but still don't really understand. Those astronomers won the Nobel Prize in 2011 for discovering that the universe's expansion is speeding up, and they made that discovery by studying the deaths of white dwarf stars billions of light years away. But let's return to July 4th, 1054, to that guest star the Chinese astronomers recorded. The Crab Nebula today is about 11 light years across and still expanding. At its center sits a neutron star, the crushed core of whatever massive sun exploded there. This neutron star spins 30 times per second its magnetic field, generating beams of radiation that sweep across space like a cosmic lighthouse. We call objects like this pulsars, and the one in the Crab Nebula is one of the most powerful known. The nebula itself glows with eerie blue light energized by the pulsar's radiation. Filaments of gas, the star's former outer layers, stream outward in chaotic patterns, each one a fossil record of the explosion's shockwave. When you look at images of the Crab Nebula, you're seeing destruction frozen in time, or rather still unfolding in slow motion. The light from that 1,000-year-old explosion still spreading, still carrying news of a star's death to the wider universe. But the Crab Nebula isn't alone. On February 24, 1987, astronomers detected a supernova in the Large Magellanic Cloud, a small galaxy orbiting our own. This was SN 1987A, and it was special. It was the closest supernova visible to the naked eye since Kepler's supernova in 1604. It was close enough at just 168,000 light years that astronomers could study it in unprecedented detail. What made SN 1987 even more remarkable was what happened 3 hours before the light arrived. Neutrino detectors in Japan and the United States recorded a brief spike in neutrino activity. 24 neutrinos detected over 13 seconds. That might not sound like much, but neutrinos barely interact with matter. Trillions pass through your body every second from the sun, and you never feel a thing. The fact that these detectors caught 24 neutrinos meant an absolutely staggering number had been released. And here's the beautiful part. The neutrinos arrived 3 hours before the light. Not because neutrinos travel faster than light, they don't, but because they escaped from the star's core the moment it collapsed. The light had to fight its way out through thousands of kilometers of dense stellar material, while the neutrinos just slipped through as if nothing was there. For the first time in history, humans had detected the moment of a star's core collapse, not by seeing it, but by catching the ghost particles it released in its death throes. SN 1987. A taught us something else, something unexpected. The star that exploded was Sanduleak, minus 69 degrees, 202, a blue supergiant. According to theory at the time, blue supergiants shouldn't go supernova. They're too hot, too stable. Red supergiants were supposed to be the ones that exploded. But there it was, undeniable evidence that our understanding was incomplete. The universe had surprised us again, teaching us that reality is always more complex than our models suggest. The remnant of SN 1987. A continues to evolve. The expanding gas has now crashed into material the star shed before it exploded, creating a glowing ring of shocked gas. In a few thousand years, it will look like the Crab Nebula does now. A beautiful, chaotic cloud of elements slowly dispersing into the interstellar medium, ready to be incorporated into new stars, new planets, maybe even new life. Think about what that means. The atoms in your body have been through this cycle multiple times. They've been inside, stars been expelled, and supernovae drifted through space as coal dust collapsed into new stars, been expelled again. Some atoms in your body might have been through 5 or 6 different stars before ending up in the cloud that formed our solar system 4.6 billion years ago. You are not made of pristine material. You are recycled stardust elements that have lived many lives before becoming part of you. There's something profound in that. Something that connects us to the universe in a way that's not metaphorical, but literal. We are not separate from the cosmos. We are the cosmos rearranged into a form that can think, that can wonder, that can look up at the stars and recognize our origins. Here's a common misconception about supernovae, that they destroy everything around them. It's true that if you're close enough, a supernova will sterilize your solar system. But close enough is relative. A supernova would need to happen within about 30 light years to seriously threaten Earth. And there are no stars near us massive enough to go supernova. The closest candidate is probably Betelgeuse, 642 light years away. When it eventually explodes, and it will probably sometime in the next 100,000 years, it will be spectacular. It might briefly become brighter than the full moon, visible during the day, a jewel in the night sky for months. But it won't hurt us. Distance once again protects us. What supernovae do destroy, they also create. The shock wave from a supernova compresses nearby gas clouds, triggering the collapse that starts new star formation. Our own sun might owe its existence to a nearby supernova that compressed the molecular cloud we formed from. The explosion that killed some ancient star might have been the trigger that started the process leading to you reading these words, thinking these thoughts billions of years later. The universe is efficient. It wastes nothing, not even violence. Every destruction seeds new creation. Every ending enables new beginnings. Supernovae are not just deaths. They're transformations, the universe's way of recycling, of taking old matter and giving it new purposes, new configurations, new chances to become something interesting. And speaking of recycled matter, speaking of elements created in stellar deaths, we turn now to something even more exotic. If supernovae create the heavy elements, if they scatter gold and platinum across the cosmos, where does most of that gold actually come from? The answer isn't from single stars exploding. It's from something stranger, something that requires 2 stellar remnants to find each other across the void spiral, together through warped space-time, and merge in an explosion that briefly shines brighter than anything else in the universe. We turn now to neutron star collisions, to the rare and violent events that rain precious metals across the galaxies. August 17, 2017, 8:41 a.m. Eastern Time, in Livingston, Louisiana and Hanford, Washington. 2 identical L-shaped buildings, each arm stretching 4 kilometers into the distance, both detect something extraordinary. A ripple. A tiny distortion in space-time itself, a wave so small it compressed and stretched each 4-kilometer arm by less than 1/10,000th the width of a proton. For just over 100 seconds, the signal built in strength and frequency, rising like a siren faster and faster and faster, until suddenly it stopped. 2 seconds later, a satellite orbiting Earth detected a gamma-ray burst from the same direction. Then telescopes across the planet swung into action. Optical telescopes, radio telescopes, X-ray observatories, all pointing at the same patch of sky at a galaxy called NGC 4993 130 million light years away. What they saw was unprecedented. A new point of light, glowing blue-white, fading over days to red, dimming gradually as the universe watched. Humanity had just witnessed something predicted but never seen. Two neutron stars locked in orbital embrace for perhaps 1 billion years had finally spiraled close enough to touch. And when they merged, they created ripples in space-time light across the electromagnetic spectrum, and a shower of heavy elements that would eventually spread through their galaxy like cosmic seeds. We had heard the collision. We had seen the aftermath. For the first time in history, we experienced a cosmic event with both gravitational waves and light. The universe had taught us a new way to observe, a new sense to experience reality. We were learning to hear gravity itself. Neutron stars are among the strangest objects in the universe. They're what's left when a massive star between about 8 and 20 times the mass of the Sun exhausts its fuel and collapses. The core crushes down protons and electrons forced together to form neutrons until you have an object containing one. 4 to 2 solar masses compressed into a sphere just 20 kilometers across. That's a sphere the size of a city containing more mass than the Sun. The density is incomprehensible. A teaspoon of neutron star material would weigh about 4 billion tons on Earth. More than all of humanity could lift combined, condensed into something you could hold in your palm if physics allowed, which it absolutely doesn't. The surface of a neutron star is thought to be a crystalline crust of iron nuclei, packed so tightly that it's the strongest material in the universe, billions of times stronger than steel. Below that, exotic forms of matter that don't exist anywhere else. Neutron superfluids, quark gluon plasmas, states of matter so extreme we can barely model them with our current physics. And at the very center, compressed beyond anything we can recreate in laboratories, there might be something even stranger. Free quarks, the fundamental building blocks of protons and neutrons, existing on their own, liberated by pressure so intense it breaks down the very structure of matter. These objects spin fast. Some neutron stars rotate hundreds of times per second. Imagine an object more massive than the Sun, compressed to the size of Manhattan, spinning faster than a blender. The equator of such a star is moving at a significant fraction of the speed of light. And because neutron stars have immensely powerful magnetic fields, sometimes trillions of times stronger than Earth's, this rotation creates beams of radiation that sweep across space like lighthouse beams. When those beams point at Earth, we detect regular pulses of radio waves. We call these objects pulsars, and they're some of the most precise clocks in the universe. There are pulses arriving with a regularity that rivals atomic clocks. But neutron stars don't always exist alone. Many form in binary systems, two neutron stars orbiting each other, or a neutron star paired with another stellar remnant. And when two neutron stars orbit each other, something inevitable begins. They emit gravitational waves, ripples in space-time, that carry energy away from the system. It's a slow process, barely noticeable at first. But over millions of years, over hundreds of millions of years, the orbit gradually shrinks. The neutron stars spiral closer and closer together, their orbital period decreasing their speed, increasing, locked in a death spiral that can only end one way. As they get closer, the gravitational waves get stronger. The orbit decays faster. What took millions of years at the beginning now takes thousands of years, then hundreds, then decades. In the final hour before merger, the two neutron stars are orbiting each other hundreds of times per second, each one feeling tidal forces so immense they begin to deform, stretched into egg shapes by each other's gravity. In the final second, the orbital frequency exceeds 1,000 cycles per second. The gravitational wave signal becomes a scream, a rising chirp of increasing amplitude and frequency. And then, contact. Two objects, each containing more mass than the Sun, each compressed to city size, collide at a significant fraction of the speed of light. The collision lasts perhaps 10 milliseconds, 1/100th of a second. In that instant, several things happen. The neutron stars merge their cores, combining to form either a more massive neutron star or a black hole, depending on the total mass. The collision is asymmetric, not a perfect head-on crash. so it sprays material outward in jets and expanding clouds. This ejected material, neutron-rich and intensely hot, undergoes something called rapid neutron capture, or the R process. Here's where things get beautiful. Inside the expanding debris, freed neutrons slam into atomic nuclei, adding mass, creating heavier and heavier elements in a cascade that takes seconds, but builds atoms all the way up the periodic table. Gold, platinum, rare earth elements, thorium, uranium. All the heaviest stable and unstable elements are forged not in supernovae where we once thought they came from, but in these neutron star mergers and kilonova, explosions that last days instead of weeks. The wedding ring on someone's finger, if it's gold, contains atoms that were likely created in a neutron star merger billions of years ago, somewhere in the galaxy, ejected into space, drifting for eons before being incorporated into the molecular cloud that formed our solar system. Every smartphone, every electronics device that uses rare earth elements contains matter forged in these cosmic catastrophes. We build our technology from the remnants of collisions so violent they shake the fabric of reality. GW170817. That event, detected in August 2017, gave us our first direct evidence of this process. Spectroscopic analysis of the kilonova's light showed signatures of heavy elements, exactly what theoretical models predicted. For the first time, we could point to a specific event and say with confidence that's where gold comes from. That's where platinum is born. That collision 130 million years ago in a distant galaxy created several Earth masses worth of gold, scattered it across light years, and eventually some vanishingly tiny fraction of it ended up here on our planet, in our oceans, mined and refined and worn as symbols of commitment and value. The gravitational wave signal from GW170817 taught us something profound about how to observe the universe. Before 2015, when LIGO first detected gravitational waves from merging black holes, we had only electromagnetic radiation to study the cosmos. Light in all its forms, from radio waves to gamma rays. We were like people who could see but not hear, experiencing the universe through a single sense. Gravitational waves gave us hearing. They let us detect events that produce little or no light, like black hole mergers, or events where the light is blocked by dust and gas. They opened a new window, a new way of experiencing cosmic violence. And when you combine gravitational wave detection with traditional electromagnetic observations, when you can both hear and see an event, you get something incredibly powerful. You can measure distances independently, check your assumptions, test theories in ways that weren't possible before. The simultaneous detection of gravitational waves and light from GW170817 let scientists measure the Hubble constant, the rate at which the universe expands, using a completely new method. The results agreed with other measurements, confirming our understanding, or at least most of it. But here's what many people misunderstand about gravitational waves. They're not just theoretical curiosities. They're real physical distortions of space-time. When a gravitational wave passes through you, it literally stretches you in one direction and compresses you in another, then reverses the process over and over at the wave's frequency. The effect is minuscule, far too small to feel. The wave from GW170817 changed your height by about 1/billionth the width of an atom as it passed through Earth. But it happened. Space-time itself rippled, and you rippled with it, and you never noticed. LIGO detects these ripples using laser interferometry. Each arm of the detector has a laser beam bouncing back and forth between mirrors. When a gravitational wave passes through one arm, gets slightly longer, while the other gets slightly shorter. Then they switch, oscillating at the wave's frequency. By comparing the laser light from both arms, LIGO can detect distance changes smaller than a proton's width across a distance of 4 kilometers. It's one of the most sensitive measurements ever made, like hearing a whisper from across the galaxy. The sensitivity required is staggering. LIGO has to account for seismic vibrations, trucks driving on nearby highways, waves crashing on distant beaches, even quantum fluctuations in the laser light itself. The mirrors are suspended by complex isolation systems that filter out vibrations. The entire apparatus operates in a vacuum to eliminate air turbulence. And still, most of what LIGO detects is noise, false signals, random fluctuations. The real gravitational wave signals are buried in this noise, extracted through sophisticated analysis that compares what two detectors thousands of kilometers apart see simultaneously. When both detectors see the same signal at the same time, accounting for the light travel time between them, you know it's real. When a third detector in Italy also sees it, you can triangulate, figure out which direction it came from, alert telescopes to look for the electromagnetic counterpart. The coordination required is remarkable, the technical achievement extraordinary. We've built instruments capable of detecting ripples in reality itself. Since that first detection in 2015, LIGO and its partner detectors have observed dozens of gravitational wave events, merging black holes mostly, but also several neutron star collisions. Each one teaches us something new: the masses involved, the spins, how often these events happen, what they produce. Slowly, detection by detection, we're mapping out the population of compact objects in the universe, the remnants of dead stars, the cosmic graveyard, where stellar corpses still collide. There's something humbling about this. Neutron stars are the end result of stellar evolution, the compressed corpses of suns that burned bright and died violent. And yet, even in death, they're not done. They orbit, they spiral, they merge, they create. The universe wastes nothing, not even death. Every ending becomes a beginning for something else. Think about the timeline. Two massive stars born together in a stellar nursery millions of years ago, each burning through their fuel at different rates. The first one explodes as a supernova, leaving a neutron star. The second follows perhaps 1,000,000 years later, leaving another neutron star. Now, you have two city-sized corpses orbiting each other in the wreckage of their birth cloud. For hundreds of millions of years, they dance slowly spiraling closer, emitting gravitational waves that carry away their orbital energy. The galaxy around them changes, stars form and die, planets come and go, and still these two neutron stars orbit, patient, inexorable, approaching their final moment. In the last day before, merger telescopes could theoretically detect them as a rapidly varying X-ray source, two hotspots orbiting each other faster and faster. In the last hour, the gravitational waves become strong enough for LIGO to detect. In the last second, the frequency rises to a scream, and then collision. The merger produces more energy in 1 second than the sun will produce in 1,000,000,000 years. It creates a kilonova, a brief flash of light, powered by radioactive decay of newly formed elements. It sends gravitational waves racing outward at light speed ripples that will travel for billions of years, carrying news of this violent union to anyone listening. And 130 million years later, on a small planet orbiting an ordinary star in an unremarkable galaxy, beings made of atoms forged in earlier stellar deaths detect those ripples, analyze that light, and piece together what happened. We reconstruct the collision model, the physics calculate, the masses measure the distance. We understand as much as our physics allows what occurred in those 10 milliseconds of contact. That's the true miracle. Not just that these events happen, but that we can understand them, that we can build instruments sensitive enough to detect them, that we can develop theories sophisticated enough to model them. That matter can arrange itself into forms capable of comprehending its own violent origins. The gold in wedding rings, the platinum in catalytic converters, the rare earth elements in phone screens. All of it born in moments of cosmic catastrophe, scattered across galaxies, slowly collected by gravity into new stars and planets, refined by geology and chemistry and human industry into useful forms. We wear the remnants of neutron star collisions. We build with them. We value them without knowing their origin. But now we know. Now we've seen it happen, watched it unfold across the electromagnetic spectrum and through gravitational wave detectors. We've witnessed creation through destruction, watched the universe forge elements in the most violent process nature allows. And yet, neutron star collisions, for all their violence, aren't even the brightest steady sources of energy in the cosmos. There exist objects far more powerful, far stranger, that shine not for seconds or minutes, but for millions of years. Objects where the energy source isn't fusion or gravitational collapse, but something even more fundamental, the warping of space-time itself around objects so dense that not even light can escape. We turn now from colliding neutron stars to the monsters that eat them, to quasars, the brightest sustained objects in the universe. In 1960, astronomer Alan Sandage was studying what he thought was a faint star. Nothing remarkable, just another point of light, cataloged as 3C48 coordinates, noted brightness measured. Radio telescopes had detected strong radio emissions from this location, which was odd for a star, but not impossible. Sandage took optical photographs, spectroscopic measurements, tried to understand what he was looking at. The spectrum made no sense. The emission lines, the fingerprints that tell you what elements an object contains, didn't match anything known. They appeared at wavelengths where no common elements had emission lines. Sandage was puzzled, confused. For 3 years, 3C48 remained a mystery. A star that wasn't quite a star producing light, that didn't quite fit any known physics. Then, in 1963, astronomer Martin Schmidt was studying another radio source, 3C273. He took its spectrum, looked at those same confusing emission lines, and had a realization. What if those lines weren't wrong? What if they were just shifted? Redshifted, specifically stretched to longer wavelengths by the expansion of space itself. If that was true, if those emission lines were familiar, hydrogen and oxygen lines just stretched by the universe's expansion, then 3C273 wasn't nearby. It was billions of light years away, which meant it had to be incredibly impossibly bright to be visible at all from such distances. Schmidt did the calculations. To appear as bright as it did from Earth while being that far away, 3C273 had to be outputting energy equivalent to the light of 2 trillion suns. 2 trillion, from a region smaller than our solar system. It was the most luminous object ever discovered, brighter than entire galaxies, and it wasn't a galaxy. It was something else entirely, something new. They called it a quasi-stellar radio source, a quasar. Today we know what quasars are, though knowing doesn't make them any less extraordinary. At the heart of most galaxies, possibly all large galaxies, sits a supermassive black hole. Not stellar mass, like the black holes formed from dying stars. Supermassive, millions or billions of times the mass of the sun, compressed into a region smaller than our solar system. These monsters form early in galactic history, probably from the direct collapse of massive gas clouds or from the merger of smaller black holes. They grow by accreting matter, by consuming everything that falls too close. And when a supermassive black hole feeds actively, when matter spirals inward through an accretion disk, heating to millions of degrees, through friction and compression, glowing with radiation across the entire electromagnetic spectrum, the result is a quasar, the brightest sustained objects in the universe. Some quasars are so luminous they outshine their entire host galaxy by a factor of 100 or more. You can't see the galaxy's stars at all. They're drowned out completely by the light from the central engine, from matter dying as it falls toward the event horizon. Here's what makes this so remarkable. The energy doesn't come from fusion. It doesn't come from nuclear reactions or chemical bonds breaking. It comes from gravity. Pure gravitational potential energy matter falling into a gravitational well so deep that even a small amount of mass converts to enormous energy. Einstein's equation, E equals mc squared, usually associated with nuclear reactions, applies here too. Matter falling toward a black hole converts up to 40% of its mass into energy before crossing the event horizon. Nuclear fusion, for comparison, converts less than 1%. Black holes are more efficient than hydrogen bombs, more efficient than the cores of stars. They are the most efficient engines in the universe for converting matter into energy. The accretion disk around a supermassive black hole is a violent place. Material spirals inward atoms, stripped of electrons by sheer heat, moving at significant fractions of the speed of light. The inner regions orbit the black hole hundreds or thousands of times per second. Magnetic fields thread through the disk, twisted and amplified by the rotation, becoming incredibly powerful. And sometimes these magnetic fields channel material into jets. Narrow beams of particles accelerated to 99.9%, the speed of light shooting outward from the black hole's poles, perpendicular to the accretion disk. These jets can extend for millions of light years. Millions. A single jet from a quasar can be longer than the distance between galaxies, carving through intergalactic space, creating enormous radio lobes where the jet slams into surrounding gas. The energy involved is staggering. The jets from some quasars carry more energy than all the stars in their host galaxy combined. And they can persist for millions of years, steady beams of radiation and particles visible across billions of light years. Most quasars existed in the early universe billions of years ago, when galaxies were younger, richer in gas, more chaotic. Back then, supermassive black holes had abundant fuel. Matter was plentiful. Mergers were common. The universe was a more violent place, and quasars lit up beacons shining across cosmic distances. As the universe aged, as galaxies consumed their gas reserves or expelled them through stellar winds and supernova explosions, the fuel ran out. The quasars dimmed. Most supermassive black holes today are quiet, dormant, waiting for new matter to fall within reach. Our own galaxy has a supermassive black hole. We call it Sagittarius A star, and it sits at the Milky Way's center about 26,000 light-years from Earth. It weighs roughly 4 million solar masses, and it's remarkably quiet, dim, barely active. It occasionally flares up when gas clouds or unlucky stars wander too close, but these events are minor, brief. Nothing like the brilliant quasars of the early universe. If you could see Sagittarius, a star with your eyes, it would look like a faint red glow cooler than a candle flame, almost invisible against the backdrop of stars. But Sagittarius. A star wasn't always this quiet. Evidence suggests that about 6 million years ago, our galaxy's central black hole went through an active phase. Not a full quasar, but active enough to create what we call the Fermi bubbles, enormous structures of high-energy gamma rays extending 25,000 light-years above and below the galactic plane. These bubbles are the remnants of a past outburst, a time when our black hole fed more actively, when jets or winds from the accretion disk blew material out of the galactic center at tremendous speeds. 6 million years ago, our ancestors, early hominids just beginning to diverge from other apes, lived under a sky illuminated by the afterglow of our galaxy's central monster, waking briefly from slumber. They wouldn't have seen it, of course. The light was gamma rays, invisible to eyes, and besides dust blocks, our view of the galactic center at optical wavelengths. But it happened. The black hole that now sits quiet and dark, once blazed, once fed, once demonstrated the same violent appetite that powers distant quasars. The most distant quasar we've discovered formed just 670 million years after the Big Bang. The universe was only 5% of its current age. The first stars had just begun forming. Galaxies were small, primitive, barely organized. And yet this quasar already contained a supermassive black hole weighing 1.6 billion solar masses. How did it get so large so quickly? That's one of astronomy's ongoing mysteries. Black holes grow by accretion, by consuming matter. But there are limits to how fast they can grow. Feed a black hole too quickly, and the radiation pressure from the infalling matter pushes new material away. There's a maximum accretion rate called the Eddington limit, and even at that limit, growing a billion solar mass black hole in 670 million years is difficult. Some scientists suggest these early supermassive black holes formed from direct collapse, massive gas clouds collapsing straight to black holes without ever forming stars. Others propose they grew through mergers, smaller black holes combining rapidly in the dense early universe. We don't know for certain, but we know they exist. We can see them, measure them, study their light from across cosmic time. They tell us the early universe was stranger and more dynamic than we imagined. Quasars also serve as cosmic lighthouses illuminating the universe's structure. Their light travels for billions of years, passing through clouds of gas galaxies' dark matter halos. As it travels, the light picks up absorption lines, fingerprints of the material it passes through. By studying these absorption systems, astronomers can map the distribution of matter between the quasar and Earth, tracing the cosmic web of filaments and voids that structures the universe on the largest scales. The hydrogen between galaxies, too diffuse to glow on its own, reveals itself by absorbing specific wavelengths from quasar light. This is called the Lyman alpha forest, a series of absorption lines that tell us about the density and temperature of intergalactic gas billions of years ago. Each line represents a cloud of hydrogen, a thread in the cosmic web, illuminated briefly by quasar light before the universe expanded and cooled, before the gas fell into galaxies or was pushed out by supernovae. Quasars have taught us about the universe's ionization, the epoch when the first stars and galaxies ionized the hydrogen that filled space, transforming the universe from opaque to transparent. Before ionization, neutral hydrogen absorbed most ultraviolet light, making the universe foggy, opaque beyond short distances. After ionization, the universe became clear, transparent to most wavelengths. Quasars existing shortly after this transition show absorption patterns that tell us when and how it happened, giving us glimpses into a crucial period we can't observe directly. But here's something most people don't realize: quasars aren't constant. They vary. Brightness fluctuates over days, weeks, years, sometimes dramatically. A quasar might brighten by a factor of 10 as a gas cloud, or a disrupted star falls into the accretion disk, feeding the black hole, temporarily increasing the energy output. Then, as the meal is consumed, the quasar dims again, returning to its baseline brightness. Monitoring these variations teaches us about the size and structure of the accretion disk, about how matter flows in the intense gravity near a supermassive black hole. One of the stranger quasar phenomena is called microlensing. When a quasar's light passes near another galaxy on its way to Earth, that galaxy's gravity can act as a lens, bending the light, often creating multiple images of the same quasar. But within that lensing galaxy, individual stars also create tiny lensing effects. As they move through the galaxy, they magnify and demagnify different parts of the quasar's accretion disk. By studying how the quasar's brightness changes as these stars pass in front, astronomers can map the accretion disk structure at scales too small to resolve directly, seeing details finer than the width of our solar system across billions of light years. The violence of quasars extends beyond light and jets. The radiation pressure and particle winds from an active quasar can heat gas throughout its host galaxy, preventing it from cooling and forming new stars. This is called AGN feedback, active galactic nucleus feedback, and it might explain why massive galaxies stop forming stars. The central black hole grows, becomes more active, heats. The surrounding gas blows it out of the galaxy or keeps it too hot to collapse into stars. The galaxy starves itself, the black hole's appetite, preventing new generations of stars from forming. There's an irony in this. Black holes, objects from which nothing escapes, can blow apart galaxies. The ultimate gravitational trap can generate winds powerful enough to expel matter from gravitational wells far larger than itself. Death becomes birth. consumption becomes expulsion. The universe maintains balance through feedback loops we're only beginning to understand. Think about the scale. A region the size of our solar system, containing billions of solar masses spinning so fast that its event horizon is moving at significant fractions of light speed, surrounded by an accretion disk glowing brighter than 1 trillion suns, shooting jets, millions of light years into space, visible from across the universe, influencing galaxy formation across billions of years. Quasars are not subtle. They're not quiet. They're the universe at its most excessive, most extreme, most unapologetically powerful. And we almost missed them. If Alan Sandage hadn't followed up on that radio source, if Martin Schmidt hadn't had that insight about redshift, we might have classified quasars as strange stars for decades longer. Science is like that sometimes. The universe hides its most spectacular phenomena in plain sight, waiting for someone to look closely enough, think clearly enough, make the connection that reveals hidden wonders. Today we've cataloged hundreds of thousands of quasars. We've measured their distances, their luminosities, their masses. We've studied their spectra, mapped their jets, watched them vary over time. We've used them as probes of the early universe, as tests of general relativity, as laboratories for studying matter, under the most extreme conditions. These monsters, these engines of destruction that eat stars and expel galaxies worth of energy, have become some of our most valuable tools for understanding the cosmos. But quasars, for all their power, aren't the only extreme magnetic environments in the universe. There exist objects even stranger, even more intensely magnetic, where fields reach strengths that would tear atoms apart through sheer electromagnetic force. Objects where the magnetic field is so powerful that empty space itself becomes polarized, where vacuum behaves like a solid, where physics enters regimes we can barely model. We turn now from black holes that eat to neutron stars that scream to magnetars the universe's lightning storms, frozen in stellar corpses. December 27th, 2004, 10:21 p.m. Universal Time. Satellites orbiting Earth suddenly went haywire. Solar observatories registered intense radiation. The detectors on spacecraft designed to study the sun's gentle variations were overwhelmed, saturated their instruments, screaming warnings about radiation levels far beyond anything they were built to measure. For a fraction of a second, gamma rays and X-rays flooded through the solar system with such intensity that Earth's upper atmosphere ionized its protective layers, disrupted by radiation coming not from the sun, but from far beyond. The source was eventually pinpointed SGR 1806-20A Magnetar in the constellation Sagittarius. Distance approximately 50,000 light years. The radiation that reached us that briefly overwrought our satellites and disturbed our atmosphere had been traveling for 50,000 years, which meant the event itself happened when Neanderthals still walked Earth, when our ancestors were just beginning to leave Africa, when the world looked nothing like it does now. And despite that immense distance, despite 50,000 years of dilution, as the radiation spread across space, it was still the brightest event ever recorded from beyond our solar system. In 1/10 of a second, SGR 1806-20 released more energy than the sun produces in 150,000 years. From 50,000 light years away, it disturbed Earth's magnetosphere. If it had been just 10 light years away, the radiation would have stripped half our ozone layer. At 3 light years, it might have triggered a mass extinction. This is what magnetars do. This is the violence they're capable of. When their magnetic fields, already the strongest in the known universe, suddenly shift and reconnect and release energy in ways that make supernovae look gentle by comparison. Magnetars are neutron stars, like the pulsars we discussed earlier. Same basic structure, a stellar core compressed to city-sized density beyond comprehension. Matter in exotic states that don't exist anywhere else. But magnetars have something extra. They have magnetic fields roughly 1,000 trillion times stronger than Earth's, a quadrillion times stronger. Numbers this large stop making intuitive sense, so let's try a comparison instead. Earth's magnetic field is about half a Gauss at the surface, strong enough to deflect compass needles, to protect us from solar wind to create auroras. A refrigerator magnet is about 100 Gauss, strong enough to hold paper to metal. An MRI machine uses fields up to 30,000 Gauss, strong enough to pull iron objects across rooms if you're not careful. The strongest continuous magnetic field ever created in a laboratory reached about 450,000 Gauss, and it required enormous superconducting magnets cooled to nearly absolute zero. A magnator's surface field is about 100 trillion Gauss, 100 million billion Gauss. At this strength, the magnetic field dominates everything. Atoms elongate into needle shapes, their electron clouds stretched by electromagnetic force. Chemical bonds break. Matter itself behaves differently. If you could somehow survive near a magnetar, which you absolutely could not, the magnetic field would be lethal at 1,000 kilometers away. It would disrupt the electromagnetic forces holding your atoms together. You would not die from radiation or heat. You would die because your molecular structure would cease to be stable. The magnetic field also warps the vacuum of space. Normally, we think of vacuum as empty as nothing, but quantum mechanics tells us vacuum is actually seething with virtual particles electron-positron pairs that pop into existence and annihilate in timescales so short they're allowed by Heisenberg's uncertainty principle. In a magnator's field, these virtual particles align, polarized by the immense electromagnetic force. The vacuum becomes birefringent like a crystal, with light traveling at different speeds depending on its polarization. Empty space itself gains optical properties normally associated with matter. Scientists believe magnetars form from the most rapidly rotating massive stars. When these stars collapse into neutron stars, conservation of angular momentum speeds up their rotation dramatically, like a figure skater pulling in their arms. But the collapse isn't perfectly symmetric. The star's rotation and its initial magnetic field, amplified by the collapse and twisted by differential rotation, can create a dynamo effect that generates these immense magnetic fields within the first few seconds of the neutron star's formation. Once established, the field is locked into the neutron star's structure, maintained by superconducting currents in its interior, capable of persisting for millions of years. But magnetic fields this strong are not stable. They evolve, they twist, they stress the neutron star's crust. Think of the crust as a crystalline layer of iron nuclei, the strongest material in the universe, harder than diamond, more rigid than any substance we can imagine. And yet, the magnetic field is strong enough to stress even this material, to bend it to store energy in its deformation, like a compressed spring waiting to release. Every so often, the stress becomes too much. The crust cracks, fractures, undergoes what scientists call a starquake sudden readjustment of crustal plates measured in millimeters, but releasing energy equivalent to thousands of supernovae going off simultaneously. The fracture allows magnetic field lines to reconnect, snapping like overstressed rubber bands, converting magnetic energy into radiation and particle acceleration in an explosion we call a magnetar flare. Most magnetar flares are relatively small, if you can call anything involving more energy than the sun produces in years small. These minor flares happen every few weeks or months, brief bursts of X-rays and gamma rays lasting milliseconds, detectable by our satellites, but not particularly disruptive. The magnetar settles the magnetic field, reconfigures slightly, and quiet returns until the next fracture. But giant flares like the one from SGR 1806-20 in 2004 are different. These are rare catastrophic events where a major starquake triggers massive magnetic field reconfiguration. We've only observed 3 giant magnetar flares in the modern era, one in March 1979 from SG R0, 526-661 in August, 1998 from SG R1900 +14, and the 2004 event from SG R180 6-20. Each one was brighter than the one before. Each one taught us something new about extreme physics. The 1979 event was actually the first evidence that magnetars existed at all. Before then, astronomers had a category of mysterious objects called soft gamma repeaters, or SGRAS sources, that produced brief gamma-ray bursts every few months. Unlike the gamma-ray bursts from distant galaxies that we discussed earlier, these bursts repeated from the same location, which made no sense if they were from exploding stars. The March 1979 giant flare was so bright and so clearly associated with a supernova remnant that it forced astronomers to reconsider. Maybe these weren't explosions at all. Maybe they were something stranger. Neutron stars with magnetic fields powerful enough to crack their own crusts. The theory was controversial at first. Magnetic fields that strong seemed impossible, or at least improbable. But as more SGRs were discovered, as their properties were measured, as theoretical models improved, the magnetar hypothesis became increasingly compelling. By the late 1990s, it was widely accepted, and the 2004 giant flare from SG R1806-2 sealed the case. Nothing else could explain the energy release, the brief duration, the repeating nature of the events. Here's what makes the 2004 flare particularly remarkable: its effects on Earth. The initial burst lasted just 0.2 of a second, but in that time, it released as much energy as the sun produces in 250,000 years. The gamma rays hit Earth's upper atmosphere, ionizing the ionosphere so dramatically that it interfered with radio communications. The lower ionosphere, which normally only ionizes during the day from solar radiation, suddenly became ionized at night. Long wavelength radio signals, which depend on reflecting off the ionosphere, were disrupted worldwide. Satellite instruments were overwhelmed. Some were temporarily blinded. Others went into safe mode, shutting down to protect themselves from the radiation assault. Scientists studying the event had to piece together data from multiple sources because no single instrument could capture the entire event without saturating. It was too bright, too intense, too far beyond what we designed our instruments to detect. And this happened from 50,000 light years away. Imagine if SG R1806-2 were closer. If it were within 10 light years, the flare would have delivered radiation doses lethal to exposed organisms. The ozone layer would have been severely damaged, possibly destroyed on the side of Earth facing the flare. UV radiation from the sun would have sterilized the surface. Ocean food chains would have collapsed. It would have been an extinction event, caused not by something happening in our solar system, but by a stellar corpse flickering briefly in a distant part of the galaxy. Fortunately, we know of no magnetars close enough to threaten Earth this way. The nearest confirmed magnetar is about 9,000 light-years away, far enough that even a giant flare would be spectacular, but not dangerous. We can observe these events, safely study them, learn from them without risking harm. Distance, once again, is our shield. But here's something worth considering. Magnetars are relatively short-lived, at least by cosmic standards. The intense magnetic field generates radiation, which carries away energy, which causes the field to decay. Within about 10,000 years, maybe 100,000 at most, the magnetic field weakens enough that the magnetar becomes a regular neutron star, a pulsar spinning quietly in the dark. Which means magnetars represent just a brief phase in a neutron star's life, a teenage rebellion of stellar corpses, violent and intense but temporary. This explains why magnetars are rare. At any given time, our galaxy probably contains only a few dozen active magnetars out of hundreds of millions of neutron stars. They're the young ones, The recently formed, the ones still cooling from their violent births, still settling into stability. Most neutron stars have already passed through this phase. Their fields have decayed. Their crusts have stopped quaking. They spin peacefully, perhaps pulsing with radio waves, but no longer capable of the dramatic outbursts that define magnetars. There's something poignant about this. Even objects as extreme as magnetars, as violent and powerful as they are, eventually calm down. The universe's rage is not eternal. Given enough time, even the angriest stellar remnants find peace. Energy dissipates, magnetic fields fade, rotation slows. What was once a source of the most intense electromagnetic storms in the cosmos becomes just another faint point in the galactic census of neutron stars. The study of magnetars has implications beyond just understanding neutron stars. These objects test our understanding of physics in regimes we can never hope to recreate on Earth. The strength of their magnetic fields, the density of their interiors, the speed of their rotation, all of these push our theories to their limits. General relativity, quantum mechanics, nuclear physics, all are needed to fully describe what happens in and around a magnetar. They're natural laboratories for extreme physics experiments we could never conduct ourselves, but which the universe provides freely for observation. Scientists have learned about the equation of state of nuclear matter by studying how magnetars rotate and respond to starquakes. They've tested predictions about how magnetic fields affect vacuum by analyzing polarization and magnetar radiation. They've explored how matter behaves at densities where atomic nuclei touch, where neutrons flow as superfluids, where quarks might exist freely rather than bound into protons and neutrons. Every observation refines our models, improves our understanding, reveals new questions we hadn't thought to ask. Do you ever wonder what it would look like to see a magnetar flare directly, not through instruments, not as graphs and data, but with eyes? If eyes could somehow survive and process gamma rays, the magnetar surface would crack fissures opening in that crystalline iron crust. Magnetic field lines, normally invisible, would snap and reconnect. And in that reconnection, the space around the magnetar would erupt with light. Not gentle light, violent, intense, searing light across wavelengths that would cook anything nearby. The neutron star itself might oscillate its shape, pulsing as starquake waves propagated through its structure. And then, as quickly as it began, it would end. The magnetic field would stabilize, the crust would settle, and the magnetar would return to its baseline fury, which is still extraordinary, but at least not catastrophic. These events remind us that the universe's violence operates on scales we struggle to comprehend. A crack in a neutron star's crust, a shift measured in millimeters, releases more energy than our sun will produce in millennia. A magnetic field, invisible and intangible, can stress and fracture the hardest matter in existence. And all of this happens in objects the size of cities, spinning hundreds of times per second, thousands of light years away in the dark. Yet this isn't even the most violent thing two stellar corpses can do. We've seen neutron stars collide, creating gravitational waves and scattering gold across galaxies. But there exists something even more fundamental, even more extreme: the merger of objects so dense that nothing, not even light itself, escapes their grasp. We turn now from magnetic storms frozen in stellar flesh to the events that literally shake space-time, to black hole mergers, to the collisions that proved Einstein right and taught us to hear the universe in entirely new ways. September 14th, 2015, 5:51 a.m. Eastern Daylight Time. In Livingston, Louisiana, a laser beam traveling through a 4-kilometer vacuum tube shifted by less than 1/10,000th the width of a proton, 1,000th the size of an atomic nucleus, a distance so small it defies comprehension. 7 milliseconds later, in Hanford, Washington. 3,000 kilometers away, an identical detector registered an identical shift. The signals match perfectly, accounting for the light travel time between sites. This was not an error. This was not noise. This was real. For the first time in human history, we had directly detected gravitational waves ripples in the fabric of space-time itself, caused by an event so violent, so energetic, that it literally shook the universe. Two black holes, each roughly 30 times the mass of the Sun, had collided 1.3 billion light-years away. The merger converted 3 solar masses, 3 entire suns worth of matter, into pure gravitational radiation in less than a second. That energy, equivalent to all the light from all the stars in the observable universe combined, radiated outward not as photons, but as ripples in space-time, traveling at the speed of light, unimpeded by matter or fields, or anything else, until finally, after 1.3 billion years of travel, they reached Earth and squeezed and stretched our detectors by less than the width of a proton. We had heard the universe scream, and in doing so, we proved Einstein right a century after he predicted gravitational waves were possible. Black holes are perhaps the most extreme objects possible within our current understanding of physics. They're regions where gravity is so intense that space-time curves back on itself, creating boundaries called event horizons, beyond which nothing, not even light, can escape. Once something crosses the event horizon, it's gone from our universe fallen into a singularity where our equations break down, where the known laws of physics cease to apply in ways we can calculate. Einstein's general relativity predicted black holes in 1915, though Einstein himself doubted they could actually exist. The math worked, the equations were elegant, but surely nature wouldn't allow something so extreme, so absolute. Carl Schwarzschild found the first exact solution to Einstein's field equations just months after they were published, describing what we now call a non-rotating black hole. But for decades, these remained mathematical curiosities, solutions to equations, rather than real objects you might find in the universe. Then, in the 1960s and 70s, astronomers began finding evidence. X-ray binary systems, where visible stars orbited invisible companions, far too massive to be anything but collapsed objects. Cygnus X1 was the first strong candidate, a blue supergiant star orbiting something with at least 10 solar masses that produced no light of its own. The only explanation that fit was a black hole matter spiraling into oblivion, heating to millions of degrees in the accretion disk, emitting X-rays before disappearing forever beyond the event horizon. But stellar mass black holes formed from individual dying stars aren't what collided in 2015. GW150914, as that first detected event was designated, came from black holes too massive to have formed from single stars. Scientists suspect these might have been second-generation black holes, formed when earlier black holes merged with neutron stars, or other black holes growing larger through cosmic cannibalism. Or they might have formed in the dense cores of ancient star clusters, where stellar remnants sink to the center, through gravitational interactions, eventually merging into more massive objects. The details of how they formed matter less than what they did. Two black holes locked in mutual orbit, spiraling closer over millions of years as gravitational waves carried away their orbital energy. Slowly, at first imperceptibly, each orbit removing minuscule amounts of energy, the separation shrinking by fractions of millimeters per year. But gravitational wave emission increases dramatically as objects get closer and move faster. What took millions of years in the beginning took thousands in the middle, then years, then months, then days. In the final hours before merger, the black holes were orbiting each other several times per second, each one feeling the other's gravitational pull, their event horizons beginning to distort, stretch toward each other like drops of water being pulled together. The gravitational wave frequency matched the orbital frequency in the range detectable by LIGO, rising in pitch as the orbit accelerated, creating what physicists call a chirp, a rising tone that increased in both amplitude and frequency until the moment of merger. That final moment lasted about a fifth of a second. 20 orbits, 20 times around each other as space and time themselves warped and rippled and screamed. Then contact. The event horizons merged two black holes becoming one, the final black hole weighing 62 solar masses instead of the combined 65. Those three missing solar masses, more than the mass of our sun, tripled converted entirely to gravitational wave energy, radiated outward in a pulse so powerful that for that brief instant, the merger produced more power than all the stars in the observable universe combined. Not light. Light is electromagnetic radiation photons carrying energy. This was space-time itself, oscillating the very fabric of reality, rippling outward at light speed, carrying energy in a form that nothing can shield or block or absorb except another gravitational field. The waves passed through Earth as if we weren't there, gently squeezing and stretching space in alternating directions, changing the distance between LIGO's mirrors by less than a proton's width, then passing on unchanged, continuing their journey through the universe forever. The detection was accidental, in its timing almost miraculous. LIGO had just finished a major upgrade and was conducting engineering tests not yet in official observing mode. The detectors were running, but scientists were still calibrating, checking systems, making sure everything worked. When the signal appeared, they initially thought it might be a test, a deliberately injected signal to verify the analysis pipeline. But it wasn't. It was real. The universe had gifted humanity with the clearest possible gravitational wave signal just days after we finished building instruments sensitive enough to detect it. In the years since LIGO and its European counterpart Virgo have detected dozens of black hole mergers, each one unique. Different masses, different distances, different orientations relative to Earth. Some face on where we observe the orbital plane directly producing clear, strong signals. Others edge on where the waves are polarized differently, creating more complex patterns. Each detection refines our understanding of how black holes form, how they merge, how common they are. What we've learned is surprising. Black holes merge far more frequently than many scientists expected. Somewhere in the observable universe, black holes are colliding roughly once every 15 minutes. The universe is filled with these events, constant, ongoing, creating gravitational waves that wash over us continuously. Most too weak or too far away to detect, but present nonetheless, a constant background hum of merging remnants. The implications are profound. Before gravitational wave astronomy, we could only study objects that emit light or other electromagnetic radiation. Black holes, by definition, don't emit light. We could infer their existence from how they affect nearby matter, from accretion disks and jets and gravitational lensing. But we couldn't observe the black holes directly. Gravitational waves change that. Now, we can detect black hole mergers and empty space events that produce no light at all, objects we could never have known about through traditional astronomy. This is like gaining a new sense. Imagine living your entire life able to see but not hear, experiencing the world purely through vision. Then suddenly sound becomes available. Music, voices, thunder, a completely different way of experiencing reality, revealing phenomena invisible to your other senses. That's what gravitational wave astronomy represents. A new window into the universe, showing us events and objects previously hidden. The waves themselves teach us about gravity in its most extreme regime. When black holes merge space-time near the event, horizons becomes intensely warped, curved to degrees that don't exist anywhere else. The gravitational waves carry information about this warping and coding, details about the black hole's masses, their spins, their final merger. By analyzing the waveform, scientists can reconstruct what happened 1.3 billion years ago with remarkable precision. And here's something beautiful. The waves confirm Einstein's predictions with extraordinary accuracy. General relativity, formulated in 1915, has passed every test we've thrown at it for over a century. But until 2015, we'd never tested it in truly strong field conditions, in regions where gravity warps space-time significantly. Black hole mergers provide exactly those conditions, and the waves they produce match Einstein's predictions perfectly. The theory works. Reality behaves the way Einstein's equations say it should, even in the most extreme environments we can observe. But gravitational waves also reveal mysteries. Some of the black holes we've detected are heavier than we thought stellar collapse could produce. The limit for a stellar mass black hole formed from a single star is roughly 60 or 70 solar masses. Above that, stellar processes should produce something else, or the star should lose enough mass before collapse that it can't form such a heavy black hole. Yet we've detected mergers producing black holes nearly 100 solar masses. Where did these come from? How did they form? We don't fully know yet. One possibility is hierarchical merging. A black hole forms from a dying star, merges with another black hole to become heavier, then merges again, growing through successive generations of mergers. Each generation creates heavier black holes that can merge again, building up mass over cosmic time. If this happens in dense stellar environments like globular clusters or galactic nuclei, where black holes can find each other and merge repeatedly, you might build up surprisingly massive objects. Another mystery, the spin. Black holes can rotate, and the rate of rotation affects how they merge, what gravitational waves they produce. Some mergers show black holes spinning rapidly, others slowly, with seemingly random orientations. This tells us something about their formation and history, but we're still piecing together the full picture. Each detection adds data points, but the full story remains incomplete. There's also the question of what exists inside the event horizon. General relativity predicts a singularity, a point of infinite density where space-time curvature becomes infinite, where our equations produce nonsense. But most physicists suspect this is a limitation of our theory, not reality. Quantum mechanics should become important at extremely small scales, and a complete theory of quantum gravity, which we don't yet have, would probably replace the singularity with something less infinite, more physical. But we can observe inside event horizons. The waves come from outside, from the in-spiral and merger of the horizons themselves. What's inside remains speculation. Think about what LIGO accomplished. The detectors work by splitting a laser beam, sending one half down each arm of an L-shaped vacuum tube, bouncing the light off mirrors 4 kilometers away, then recombining the beams. When a gravitational wave passes through it, stretches space in one direction and compresses it in the perpendicular direction, changing the length of one arm relative to the other. This changes the phase relationship between the laser beams, creating interference patterns that reveal the tiny length change. The sensitivity required is absurd. LIGO needs to measure distance changes smaller than a proton across 4 kilometers. That's like measuring the distance to the nearest star to within the width of a human hair. Every possible source of noise must be eliminated or accounted for. Seismic vibrations from traffic ocean waves, earthquakes halfway around the world, thermal fluctuations in the mirrors, quantum noise from the laser itself. The mirrors hang from sophisticated suspension systems that isolate them from vibrations. The entire apparatus operates in ultra-high vacuum, and still false signals outnumber real ones by millions to one. That's why having multiple detectors is crucial. A real gravitational wave will arrive at LIGO Livingston and LIGO Hanford with a time delay corresponding to the light travel time between them, coming from a direction consistent with both seeing the same wave. A local disturbance, a truck passing by, or an earthquake will only affect one detector. By requiring coincidence by comparing what both detectors see, scientists can distinguish real signals from noise with high confidence. Since that first detection in 2015, gravitational wave astronomy has evolved from the experimental verification to a regular observational technique. Dozens of black hole mergers detected, neutron star collisions observed, each event teaching us something new about the universe's population of compact objects, about how these remnants form and evolve and interact. We're building a census of cosmic violence, mapping out how often these events happen, where they occur, what masses are common, what spins are typical. And we're just beginning. LIGO is being upgraded for even better sensitivity. New detectors are being built in Japan and India. Space-based detectors like LISA will observe lower-frequency gravitational waves from supermassive black hole mergers events even more energetic than the stellar mass mergers LIGO detects. In a decade or two, we might observe hundreds of mergers per year, building detailed maps of how black holes populate the universe across cosmic time. But even black hole mergers, violent as they are, aren't the beginning of the story. There was an event before any of this, before black holes existed, before neutron stars formed, before the first stars ignited. An event that created space and time themselves, that started the expansion we still observe today, that set initial conditions for everything that followed. We turn now from the violence of endings to the violence of beginning, to the moment when everything started, when the universe itself came into being. Imagine you could rewind time, not metaphorically, actually reverse the flow of moments. Watch galaxies move backward, stars unburn their fuel planets, dissolve into dust clouds. Keep going, further back. The universe gets smaller, denser, hotter. Galaxies merge, blur together into a sea of hydrogen and helium. Stars wink out of existence. Atoms break apart into their component particles. Space itself contracts, pulling everything closer together. Temperatures rising, densities increasing beyond anything that exists in the universe today. Keep rewinding. 13 billion years, 13 and a half. The universe becomes the size of a galaxy, then a solar system, then a room, then a grain of sand. And still you keep going back to a moment so extreme, so fundamental that time itself begins there. Before that moment, before has no meaning. There is no space to contain events, no time to order them. There is only the beginning, the Big Bang. Not an explosion in space, an explosion of space. The moment when everything started. Here's the most common misconception about the Big Bang. People imagine it as a blast occurring at some location, matter flying outward from a central point into pre-existing empty space, like a bomb going off. This is completely wrong. The Big Bang happened everywhere simultaneously. Every point in space was part of it. There is no center, no edge, no place where it happened more than anywhere else. When we say the universe is expanding, we don't mean things are moving through space away from some origin point. We mean space itself is stretching, carrying galaxies apart, like dots on an inflating balloon. The balloon analogy works if you think about its surface, not its interior. Imagine tiny ants living on the balloon's surface. They can't move up or down into the balloon, only across its two-dimensional surface. As you inflate the balloon, the ants see every other ant moving away. The farther apart two ants are, the faster they separate because there's more stretching rubber between them, but there's no center on the surface where the expansion starts. Every point is equivalent. That's our universe, except in 3 dimensions instead of 2. The evidence for the Big Bang is overwhelming, accumulated over decades from multiple independent sources. It started with Edwin Hubble in 1929, observing that distant galaxies showed redshift. Their light stretched to longer wavelengths. The farther away a galaxy was, the more its light was redshifted. Hubble interpreted this as motion. Galaxies were moving away from us, and more distant ones were moving away faster. This relationship, now called Hubble's law, suggested the universe was expanding. If it's expanding now, it must have been smaller in the past. Rewind far enough, and everything must have been together, infinitely dense, infinitely hot. But the real confirmation came in 1964 accidentally. 2 radio astronomers, Arno Penzias and Robert Wilson, were trying to eliminate noise from their antenna at Bell Labs in New Jersey. They kept detecting a persistent hiss, a microwave signal coming from all directions, equally about 3 degrees above absolute zero. They couldn't explain it. They cleaned the antenna, they checked the electronics, they even removed pigeon droppings thinking maybe that was causing interference. Nothing worked. The signal remained. Unbeknownst to them, just a few miles away at Princeton University, physicist Robert Dicke had predicted exactly this signal. If the universe began in a hot, dense state, it would have been filled with intense radiation. As the universe expanded and cooled, that radiation would have stretched to longer wavelengths, cooling with the expansion. By now, about 13.8 billion years after the Big Bang, that primordial radiation should have cooled to about 3 Kelvin, appearing as microwave background radiation, filling all of space. Penzias and Wilson had discovered it. The cosmic microwave background, or CMB, the afterglow of creation still washing over us from every direction. For this discovery, they won the Nobel Prize in 1978. And cosmology, the study of the universe's origin and evolution, transformed from philosophical speculation into rigorous observational science. The CMB tells us an extraordinary story. It shows us what the universe looked like 380,000 years after the Big Bang, when it cooled enough for atoms to form, when light could finally travel freely through space. Before that moment, the universe was opaque, a hot plasma where photons constantly scattered off free electrons, unable to travel any distance before interacting again. When atoms formed, when electrons bound to nuclei, the photons were released free to travel unimpeded across the cosmos. Those photons released 13.8 billion years ago have been traveling through expanding space ever since. By the time they reach us, they've been stretched from visible light to microwaves cooled from thousands of degrees to just 2.7 Kelvin above absolute zero. But they carry information about conditions at the moment they were released, encoded in tiny temperature variations across the sky. These variations, measured to be about 1 part in 100,000, represent the seeds of all structure in the universe. Slightly denser regions where gravity would eventually pull matter together to form galaxies, stars, planets, us. Satellites like COBE MAP and Planck have mapped these temperature variations in exquisite detail. The pattern they reveal matches theoretical predictions with stunning precision. The universe is 13.8 billion years old. It's composed of about 5% ordinary matter, the atoms that make up stars and planets and people. About 27% is dark matter stuff that interacts gravitationally but doesn't emit light. And about 68% is dark energy, the mysterious force driving the universe's accelerating expansion. These numbers come from analyzing the CMB's temperature fluctuations, from how the pattern of hot and cold spots statistically distributes across the sky. But what happened in those first moments before atoms formed, before the CMB was released? The physics gets increasingly extreme, increasingly speculative as we approach the initial instant. Yet observations and theory together paint a remarkable picture. In the first second after the Big Bang, the universe underwent phases of evolution stranger than anything existing today. The first fraction of a second, perhaps the first 10 to the power of minus 32 seconds, may have involved cosmic inflation, a period of exponentially rapid expansion driven by a quantum field we still don't fully understand. In less time than it takes light to cross a proton, the universe expanded by a factor of at least 10 to the power of 26, smoothing out initial irregularities, setting the stage for everything that followed. After inflation, the universe was filled with incredibly hot, dense quark-gluon plasma, the same state of matter we briefly create in particle accelerators, but existing everywhere, filling all of space. As expansion continued, the universe cooled. Quarks combined into protons and neutrons. For a few minutes, conditions were right. For nuclear fusion forging the lightest elements, hydrogen fusing into helium, small amounts of deuterium, lithium, beryllium. This is called Big Bang nucleosynthesis, and the ratios of elements it predicts match what we observe in the oldest stars, in regions of space that haven't been enriched by stellar fusion. About 75% of ordinary matter became hydrogen. About 25% became helium. Trace amounts of other light elements, everything heavier than lithium, came later forged in stars and supernovae, and neutron-star collisions scattered across space eventually incorporated into planets and life. But that primordial ratio, 3/4 hydrogen, 1/4 helium, comes directly from the Big Bang's first 3 minutes. After the first few minutes, the universe was too cool for fusion. For the next 380,000 years, it remained a hot plasma cooling gradually as it expanded, but still too hot for atoms to form. Then, as temperatures dropped below a few thousand degrees, electrons and nuclei combined. Atoms formed. The universe became transparent. The CMB was released, and matter began its slow collapse into the structures we see today. The first stars probably formed a few 100 million years after the Big Bang, massive and short-lived, burning hot and dying young, enriching space with the first heavy elements. The first galaxies assembled from merging clusters of these early stars, growing through hierarchical structure formation, smaller objects merging into larger ones over billions of years. Our own Milky Way is built from hundreds of smaller galaxies that merge together over cosmic time, their stars and gas combining into the spiral structure we see today. One of the strangest aspects of Big Bang cosmology is what it says about the universe's geometry and extent. Based on our measurements, the universe appears to be spatially flat, meaning parallel lines stay parallel forever. Angles and triangles sum to 180 degrees, the familiar geometry of Euclidean space. A flat universe extending infinitely would mean the Big Bang happened everywhere, not at a point. The universe has always been infinite in size, just with different density and temperature at different times. This is hard to visualize, perhaps impossible, but it's what the mathematics suggests. If the universe is truly infinite, then beyond our observable horizon, beyond the distance light has had time to travel. Since the Big Bang, there's more universe, more galaxies, more stars, more space expanding, according to the same laws. We can never see it, never interact with it, but it exists parallel to our observable bubble, following the same physics, perhaps, with different arrangements of matter, but fundamentally similar. And here's something profound. The Big Bang wasn't the creation of matter from nothing. It was the creation of space and time themselves, the framework within which matter and energy exist. Before the Big Bang, before is meaningless. Time began with the expansion. Asking what happened before the Big Bang is like asking what's north of the North Pole. The question contains a category error, applying temporal concepts to a situation where time doesn't exist. This troubles many people. Our intuition says everything must have a cause, must come from something prior. But the universe doesn't owe us intuitive explanations. Quantum mechanics already showed us that particles can appear from vacuum fluctuations, that causality becomes fuzzy at small scales, that the universe is fundamentally probabilistic rather than deterministic. Maybe the universe's existence is similar, a quantum event writ large space and time, fluctuating into existence from nothing isn't quite the right word. From a state where our concepts don't apply. Some scientists speculate about what might have come before, using that word loosely. Eternal inflation models suggest our universe is one bubble in an ever-inflating multiverse, new universes constantly budding off each, with potentially different physical laws. Cyclic models propose the universe expands and contracts eternally, each Big Bang followed billions of years later by a big crunch, then another bang. String theory suggests extra dimensions. We don't perceive our universe, perhaps a membrane floating in higher dimensional space. These ideas are speculative, untested maybe, untestable. They're fascinating thought experiments, but not yet science in the rigorous sense. What we know for certain is that our universe, the observable cosmos containing hundreds of billions of galaxies, began in a hot, dense state approximately 13.8 billion years ago, and has been expanding ever since. Everything we've observed confirms this. The expansion rate, the CMB temperature, and fluctuations, the abundance of light elements, the evolution of galaxies over cosmic time, all of it fits together into a coherent picture. And that picture includes us. The Big Bang set initial conditions that allowed structure to form, allowed gravity to pull matter into stars, allowed those stars to forge heavy elements, allowed planets to coalesce, allowed chemistry to become complex enough for life. We exist because the universe began in just the right state, with just the right properties expanding at just the right rate. Change any of those initial conditions significantly, and we wouldn't be here to wonder about them. Some call this the anthropic principle. We observe the universe to have properties compatible with our existence, because if it didn't, we wouldn't be here to observe anything. It's a tautology, but a profound one. The universe doesn't need to be this way. It could have expanded too quickly for galaxies to form too slowly and recollapsed immediately with different fundamental constants that don't allow stars or chemistry or complexity. But it isn't any of those things. It's a cosmos vast and old and structured, capable of creating observers within itself. The Big Bang isn't just the most powerful event in the universe. It's the event that created the possibility of all other events that established the arena in which stars could form and die, in which black holes could merge, in which magnetars could flare and neutron stars could collide. Every cosmic violence we've discussed tonight traces back to that initial moment, to the expansion that set everything in motion. And yet, for all its power, for all its fundamental importance, the Big Bang brought the universe from ultimate simplicity to increasing complexity, from uniform plasma to atoms to stars to galaxies to us. Violence creating beauty, chaos generating order. The universe's most powerful event was also its most creative, the moment that made all future moments possible. As we drift toward the close of this cosmic journey, as the night deepens and these stories of universal violence settle into memory, we carry forward one last realization about power and silence, about how even the brightest explosions eventually fade into the quiet dark, and what that teaches us about our place in this vast, ancient, beautiful cosmos. We've traveled far tonight, you and I, from the brightest flashes since creation itself to the moment when creation began. From gamma-ray bursts that could sterilize worlds to supernovae that built those worlds atom by atom. From neutron stars crushing together to birth gold to quasars brilliant enough to illuminate the early universe, to magnetars whose magnetic fury could tear matter apart at 1,000 kilometers. From black holes merging in silence, sending ripples through the fabric of reality, to the Big Bang that wove that fabric in the first place. 7 types of cosmic violence. 7 ways the universe remembers how to scream. And yet, here we are, safe, quiet, listening to these stories from across billions of light years and billions of years untouched by the chaos, protected by the immense mercy of distance and time. There's something almost tender about that, isn't there? The universe's greatest acts of destruction become our bedtime stories. Violence transforms into wonder. Terror becomes curiosity. What could kill us in an instant instead teaches us, inspires us, connects us to the cosmos in ways our ancestors could never have imagined. Every photon that reaches our telescopes, every gravitational wave that ripples through our detectors, every neutrino that slips through our instruments, they're all messengers from events so far away, so long ago that we can study them safely. We can measure their fury without feeling their heat. We can calculate their power without suffering their consequences. We exist in a pocket of cosmic calm, a brief, quiet moment between catastrophes. And that accident of timing allows us to be observers instead of victims. Think about how improbable this is. If we'd evolved a few billion years earlier, the universe would have been too chaotic, too rich in supernovae and gamma-ray bursts, too violent for stable planetary systems to support complex life. A few billion years later, and the universe might be too quiet. Its star formation mostly finished its fuel, depleted, entering the long decline toward heat death. But we're here now, in what some astronomers call the stelliferous era, the age of stars, when the universe is old enough to have created heavy elements, but young enough to still burn bright. And in this era, we've developed the ability to look backward in time. Every photon we collect from a distant galaxy left that galaxy millions or billions of years ago. We're not seeing those galaxies as they are. We're seeing them as they were frozen moments from cosmic history preserved in light that's been traveling longer than our species has existed. When we observe a galaxy 10 billion light years away, we see it as it was when the universe was less than 4 billion years old, when our sun hadn't formed yet, when the material that would become Earth was still scattered across space in diffuse clouds. Astronomy is archaeology. We're digging through layers of time, observing different epochs, piecing together the universe's story from fragments of light. And what we've learned is extraordinary. The universe is comprehensible. The same physics that governs falling apples and orbiting planets also governs exploding stars and colliding black holes. General relativity, formulated by one person thinking deeply about gravity's nature, correctly predicts what happens when objects containing millions of solar masses merge at relativistic speeds. Quantum mechanics, developed to explain atomic spectra, describes matter in neutron star cores where density exceeds anything we can recreate. The laws we discover here in our laboratories apply across the cosmos. That's not obvious. The universe didn't have to work that way. Physical laws could have been local, changing from place to place, making distant astronomy impossible. But they're not. A hydrogen atom here emits light at exactly the same wavelengths as a hydrogen atom in a galaxy billions of light years away. The speed of light is constant. Gravity works the same everywhere. This universality of physical law is what makes science possible, what lets us interpret signals from across the universe and extract meaning from them. But there are still mysteries, deep ones. We don't know what dark matter is, the invisible substance that makes up most of the matter in the universe. We've detected its gravitational effects, mapped its distribution, confirmed it's not ordinary matter made of atoms, but we haven't identified the particles it's composed of. Dozens of experiments are searching deep underground in space at particle accelerators, trying to catch dark matter particles interacting with ordinary matter. So far, nothing definitive. The universe keeps this secret well. We don't know what dark energy is, either the mysterious force accelerating the universe's expansion. We've measured its effects with precision-used supernovae and other standard candles to track how expansion has changed over cosmic time, but we don't understand its nature. Is it a property of space itself, Einstein's cosmological constant resurrected? Is it a new field pervading the universe? Is it evidence that general relativity needs modification on cosmic scales? We don't know. We're observing an effect without understanding its cause. And we don't know what happened at the very first instant of the Big Bang, in the first 10 to the power of minus 43 seconds, called the Planck time, when quantum effects of gravity become important and our current theories break down. We need a theory of quantum gravity, a framework that unifies general relativity and quantum mechanics. But we don't have one yet. String theory is a candidate. Loop quantum gravity is another. But we lack experimental tests, ways to distinguish between theories at energies we can't reach. These mysteries are exciting, not frustrating. They mean there's more to discover, more to understand. Science isn't about having all the answers. It's about asking better questions, developing tools to investigate them, slowly expanding the island of knowledge into the ocean of ignorance. Every answer raises new questions. Every discovery reveals new mysteries. That's not a flaw in the process. That's the process working as it should. And consider what we've accomplished in just the last century. In 1920, We thought the Milky Way was the entire universe, that spiral nebulae were gas clouds within our galaxy, rather than separate galaxies billions of light years away. We didn't know about the Big Bang, about cosmic expansion, about dark matter or dark energy. We hadn't discovered neutron stars or black holes or quasars. Gravitational waves were theoretical speculation. The cosmic microwave background was unknown. Nuclear fusion in stars was barely understood. 100 years later, we've mapped the observable universe. We've detected gravitational waves from merging black holes. We've photographed black hole event horizons directly imaging the shadow of the supermassive black hole at the center of galaxy M87. We've measured the age and composition of the universe to percent-level precision. We've observed galaxies forming when the universe was less than 1 billion years old. We've found thousands of exoplanets, worlds orbiting other stars, some potentially habitable. We've landed rovers on Mars and sent probes beyond the solar system into interstellar space. The pace of discovery is accelerating. New telescopes, more sensitive detectors, better theoretical tools, all combining to reveal the universe in unprecedented detail. The James Webb Space Telescope, launched in 2021, is observing the earliest galaxies peering further back in time than ever before. LIGO and its partner detectors are cataloging mergers, building a census of black holes and neutron stars. Particle physics experiments are searching for dark matter, for new forces for physics beyond our current understanding. What will we know in another 100 years? What mysteries will we solve? What new questions will we discover? It's impossible to predict. But based on history, on the pattern of scientific progress, we can be confident that the universe will continue surprising us, challenging our assumptions, revealing wonders we can't yet imagine. And you're part of this. Not just passively listening, but actively participating in humanity's cosmic journey. Every time you look up at the night sky with wonder, every time you ask how or why, every time you seek to understand rather than just accept, you're continuing a tradition that stretches back to our earliest ancestors who looked up and wondered what those lights were, those distant fires hanging in the dark. We're all made of star stuff, as Carl Sagan beautifully put it. But we're also made of curiosity, of the drive to understand, of the capacity for awe. The universe created us, gave us eyes to see, and minds to comprehend, and now uses us to understand itself. We're the cosmos becoming conscious matter, contemplating its own nature, the universe's way of knowing it exists. The violence we've explored tonight, those 7 types of cosmic catastrophe, they're not separate from us. They're part of our lineage, our history, our very composition. Every breath you take contains oxygen forged in a supernova. Every thought firing through your neurons relies on carbon created in dying stars. The iron in your blood, the calcium in your bones, the gold in any jewelry you might wear. All of it was created in moments of extreme violence, scattered across light years, slowly collected by gravity into new stars and planets, refined by geological processes, and eventually incorporated into you. You are the universe in human form, not metaphorically, literally. Your atoms have been through multiple stellar cycles, have been inside different stars, have traveled across the galaxy, have witnessed cosmic events from the inside before becoming part of you. You carry that history in your body, in every cell, in every molecule. You're not just in the universe. You're of it, made by it, inseparable from it. And that should bring comfort, not terror. Yes, the universe is capable of unimaginable violence. Yes, there are events that could destroy Earth in an instant if they occurred nearby. But those same violent processes created the elements that make life possible, that make you possible. The universe's rage is also its creativity. Its destruction is also its construction. Death and birth aren't opposites. They're different phases of the same cosmic cycle. So, when you feel small, when the scale of the universe seems overwhelming, when 13 billion years and 100 billion galaxies make your life seem insignificant, remember this: you're made of the rarest stuff in the universe. complex, organized matter capable of thought and feeling and wonder. Most of the universe is empty space. Most of what isn't empty is simple hydrogen-helium radiation. You're extraordinary. You're improbable. You're a temporary arrangement of atoms that can somehow appreciate its own existence. And you're not alone. Every person you've ever met, every living thing on Earth, shares this cosmic heritage. We're all star children, all built from supernova remnants, all carrying the same ancient atoms rearranged into different patterns. The person sitting next to you, the tree outside your window, the bacteria in your gut, all of us are related not just biologically, but atomically, all composed of the same cosmic debris, all temporary patterns in the universe's great flow. That's the ultimate lesson from these stories of cosmic violence, creation, and destruction. Our partners, not enemies. The universe doesn't waste anything. Every ending enables new beginnings. Every catastrophe seeds future complexity. And we, improbable as we are, temporary as we are, have the privilege of existing in this moment, this cosmic instant, able to look back at the violence that created us and forward to the mysteries still waiting. The night is deep now. The stories have been told. 7 types of cosmic violence explored and understood their power, measured their beauty, appreciated. From gamma-ray bursts to the Big Bang, we've traced the universe's capacity for extreme events, for moments when physics is pushed to its limits and beyond. But knowledge is meant to be shared, and wonder grows when passed along. If these stories resonated with you, if you found beauty in the mathematics of black holes or poetry in the formation of gold, if the violence of the cosmos somehow brought you peace, then perhaps you'll share that feeling. Tell someone about the stars that died to make their atoms. Explain how we learned to hear space-time rippling. Point out that the calcium in their bones was forged in a supernova billions of years ago. The universe is vast and old and strange, but it's also ours to explore, to understand, to appreciate. Every question we answer reveals new mysteries. Every mystery we confront expands our sense of wonder. And every moment of understanding, however small, is a victory for consciousness, for the universe's ability to know itself. We've drifted together through cosmic violence and emerged with knowledge instead of fear, understanding instead of terror. The universe's most powerful events have become our teachers, showing us the extremes of what nature allows, the boundaries of physical law, the creative potential hidden in destruction. Thank you for traveling with me through these stories, for lending your attention to tales of ancient violence and modern discovery. Thank you for wondering, for questioning, for seeking to understand. In a universe capable of such extremes of such beauty and terror combined, your curiosity is a light against the dark. There are more stories waiting, more cosmic mysteries to explore, more wonders hiding in the mathematics and the observations and the quiet spaces between the stars. And when you're ready, when the next quiet night finds you seeking knowledge, told softly, these stories will be here, waiting to drift through the dark with you once more. Until then, rest well, dream deeply, and remember you're made of stardust, born from violence, capable of wonder. The universe created you to understand itself, and every moment of understanding is a small miracle in the vast cosmic dark. Sleep well, dream gently. Good night.